Yeah, good evening again to you and Catania, to you online. Here from Germany, Darmstadt. Benjamin Möller is my name. I'm coming from the Fraunhofer Institute for Structural Durability and System Reliability, LBF. So we are mainly focusing on topics of structural durability, and in this case, I would like to present you some results from investigations we performed within shipbuilding industry, especially in this case, tensile and fatigue strength investigations on laser beam welded steel aluminum adapters. And for sure, we know that steel and aluminum joining is always a point of discussion, but we will get some insight here today. So I will start with the motivation and background, then go over to so-called crossing beam welds, so lap joints in general, which formed the basis for this investigation, and then move over to steel aluminum adapters, which are the main focus here. So you can see one of them on the right side immediately, and then give some final conclusions. Okay, yeah, these laser beamed adapters aim to be a semi-finished product when joining steel to aluminum for the ship industry and applying material closure and form fit in combination using an undercut. So it's not just a metallurgical closure, which we have in this case, but also a form fit. The basic investigations then were to design a geometry between steel and aluminum, including such a crossing beam situation to realize strength improvement. And the basis was already existing some first investigations on such steel aluminum joints and finally leading to assessment of static and fatigue strength here. The motivation is given from the shipbuilding industry, especially the design and construction of yachts, where it is very often the case that there is a ship hull, which is made out of aluminum, and there is a ship deck, which is made of aluminum, and a ship hull structure, so base structure, which is made of steel. And then in the intersection, we need a joining of steel and aluminum. This is actually realized by so-called explosion welding. So joining an aluminum plate and a steel plate by explosion welding process. In this process, we also need technical pure aluminum layer in between these two, which limits the strength. And then from this, there is a design and welding through aluminum structure and a steel structure to be implemented in such a ship structure. So our starting point was how could be an adapter made of steel and aluminum look like, which is to be used in laser beam welding. And therefore we had a first conceptual study giving some outcomes and then performing first finite element simulations before moving over to fatigue testing and validation. However, I will first start here with a basic investigation. So we know that we have two very different materials when we try to join steel to aluminum. So in this specific case, we joined S355, which is relevant for the shipbuilding industry, at least in terms of strength. And the corresponding aluminum material was ENAV, so aluminum alloy 6082 in heat-treated state. And already from these yield strength, tensile strength, and elongation, we see that they are quite different materials, but also in terms of heat transfer, these materials are quite different. So this usually leads, when joining by welding, to formation of intermetallic faces. Some of them are quite brittle, so they lead to cracks and are critical for fatigue failure. And then we have also some cracks in the intersection between steel and aluminum. So we see it here, which is not a perfect joining between these two materials. Then you get already cracks inside it, while if there is a more or less good joining process, you can avoid most of the cracks and also most of the brittle intermetallic faces. However, resulting strength limitations might occur. And the question is then, what is our loading scenario? So in case of such a shear loading, there already a form fit exists so that the strength is quite or is comparably high, while when we apply such an orthogonal loading, which leads to peel stresses in between the sheets and some bending components, the strength is much lower. Therefore, we started with a initial investigation how such a crossing beam weld could look like in terms of local welding and geometry parameters. So how should this joining of steel material, so the upper part should be made of steel, as you can see here, and the lower one, in this case green one, would be the aluminum, and we are mainly welding from the top with two crossing beams into the material, and then we get some kind of geometry between steel and aluminum material, which could have such an edge shape or more a round shape. We need to decide whether there is more a contact between these two materials, or if there is more an ideal tie, which would mean that we have a fully metallurgical joining between the two materials, which is never perfectly the case. However, contact would be more or less the worst case scenario over here. And we have the two loading directions, which I explained before. And starting with this, we set up a matrix of parameters to be investigated, so that quite a huge amount of variance and finite element models resulted to be evaluated in these finite element simulations. And we performed this and already realized that such a complete tie between the two materials would not give major information in terms of stresses and strains. So this would be a perfect, more or less perfect solution. But approaching such a contact situation, so not a perfect metallurgical combination of steel and aluminum, would lead to quite high stresses and strains in the area in between the two sheets at the steel material. So from this, we said there is a path along the intersection of the two materials, and we can evaluate stresses and strains from it. Especially strains are of interest in the aluminum material and the steel material. So blue is aluminum peak of maximum strain, orange is maximum strain of the steel material. And if we evaluate this for all of the finite element models and simulations, we get some matrix box plots, as you can see it here. So we have the depth of the weld geometry. We have the width of the weld geometry, and we have the angle, which could be varied. And we see in color then the strains resulting from the finite element simulation. So dark blue is higher strains, green and light yellow is lower strains, which give us the first information where, in which configurations beneficial weld geometries result, so that we can say increased penetration depth leads to decreased strains, for example, and an increased angle to a certain amount also leads to decreased strains. And coming from this, we went into first testing, so with some optimized parameters, in this case, then decided for welding speeds of 0.75 meters per minute down to 0.65, so not a quite wide range, and penetration depths resulting from this between 2.5 to or 2.0 to 3 millimeters. These tests were then performed in a servo-hydraulic test rig under these orthogonal bending loading, as we called it. So pushing away the two sheets from each other and coming to a final failure where cracks initiated from the root towards the steel material due to this bending of the two sheets. The test frequency was 5 Hertz in this case, so load controlled, and we can see from one second, from the video then how the strains by application of digital image correlation localized in the critical areas, as you already can see here before final rupture, and then it comes to the point 10%, 5% before the final rupture that there is quite a high stress concentration. And yeah, evaluating this then in an SN diagram now, using the bending stress amplitude towards cycles to crack initiation. So as we can see from these digital image correlation, digital image, that around 90% to 95% of the final rupture, we have a stress localization correlating with the crack initiation, and including the different variants we investigated here with the penetration depths 2.0 to 3.0, we see that they are more or less in the range of the scatter of one single SN curve evaluated here. Yeah, with the potential knee point, but not necessarily. And with this information, we went into design of such an adapter as already introduced. So in this case, then not just a single lap joint, but welding from both sides, steel sheets to an aluminum profile in this case, and then for investigation, cutting this more than 1 meter long adapter, which could be applied into small pieces of test specimens. The welding angle decided here was 15%, so not too high, but too high angles were not able to process in this case, so would be lead to to a process which it was not realizable. And then we had welding speeds here between, in the same range as before, more or less 0.75 meter down to 0.5 meter per minute, double laser power of 2 times 6 kilowatts. And what is also quite essential is the aluminum content in the tip part of this weld, which should be below 10%. In this case, we found it to be 6%, which gives us a quite good microstructure there. So then we went into static testing, in this case also with these welded additions to it. So we have the steel part up here with a steel gas metal arc weld on the top, and aluminum part down here with the I'm not sure, it could be a gas metal arc weld as well, and realized that our adapter is capable to reach quite high force amplitudes, which are above the yield strength of 5000 aluminum alloy, and having then a final rupture in this aluminum weld, so not in the adapter specimen itself. Not just therefore, but also due to this reason, we went over to fatigue testing. In this case, so load controlled fatigue testing, actual force as it was in the more or less in the tensile test as well. So on the aluminum side and on the steel sheet side. And we included the parameter variations shown before as well. So different welding speeds here, leading to different penetration depth of the local weld geometry, and finding more or less the same as we had it for these cross-beam specimens, that within the scatter, these parameters do not give a trend towards one of the welding speeds, for example. And in addition, what we found is in comparison with previous investigations on quite similar adapters, but not having these crossing beams, that the fatigue strength is much increased in a factor of 3 to 5 in this case. And yeah, additionally, investigations for the ship industry is usually also the corrosion fatigue testing. So having a corrosion solution, in this case, natrium chloride, 5% solution, additionally added during fatigue testing, and this usually decreases the fatigue strength in the high cycle and towards the very high cycle fatigue regime. However, in our 3 tests which we performed here, there was no decrease in fatigue strength related to the corrosion fatigue visible. And then there was also the simulation of these adapters to get information on the local stress hotspots on the one hand side, but also to identify optimization potential. So we've realized from the simulation already that we have a lateral bending of the steel sheets here, which is caused by the loading situation, and which gives us additional stresses on the hotspot at the aluminum material. Therefore, the idea was to modify this aluminum part and add some lateral fixture to the steel, so that the bending is avoided, and this could be shown already in the numerical simulation results, and reduced the stresses at the aluminum hotspot significantly. With this, we then also went in the validation of these steel to aluminum adapters. So we see the physical realization here to the bottom left. And the same situation, which is not true, is the NaCl solution here. It's an air, tested in air in this case, with and without this support structure. And we could see that these reduction of the local stresses in the aluminum material, which leads to a rupture here in this part, increases the fatigue strength related to this aluminum profile modification. And with this, I come to the conclusions of my talk. So we investigated here laser beam welded steel aluminum adapters. First, starting with a parametric FE simulation on crossing beam welds to define the weld geometry design for such an adapter. Then we investigated these crossing beam welds under orthogonal loading, which is the critical one, and found or showed the positive effect of this form fit of the crossing beams. We have seen that the digital image correlation is quite a valuable method for the analysis of the local strain field and then for crack initiation as well. Under tensile testing, there was not so much information on the cracks of such an adapter, since the final rupture was in the aluminum weld outside. However, under fatigue testing, then the root notch between the sheets led to a fatigue failure. We showed that a factor of 3 to 5 towards previous designs is realizable, and that it is quite a stable adapter towards welding process parameter variations. Finally, there was no negative effect of corrosive media on these adapters, and optimization of it could already lead to, or finally lead to 30% of improvement of the fatigue strength of it. With this, I thank the German Federal Ministry for funding of this project, and you for your attention. Thank you, and I'm open for questions.